Okay, question 4. Here's a piston moving it in a cylinder. There you're given an equation, D equals -4 cosine 220t for the displacement. Now what does that mean initially? What it tells us is we've got omega to be 220, which means we can calculate the period very easily, or the frequency of motion. We're also given the amplitude, the maximum displacement, to be -4 at time 0. So that means it starts exactly as shown in this position right here. So that's where it starts at time 0. How do we know that? Well, if t is 0, cosine of this is 1. So at time 0, d equals -4. Now then, the first question. State the distance between the lowest position, AB, and the highest position, CD, of the top surface of the piston. Now, since we know that the midpoint is somewhere here, and that this initial distance is the amplitude, which is -4.0, this must be a positive 4.0 away from the equilibrium. So, of course, the combined distance, that is the distance we're after, 8 centimeters between the two lines. Part 2, determine the number of oscillations made per second by the piston. In other words, they're asking us to find the frequency. Now we know that is equal to 2 pi, sorry, that's not quite correct, is it? Oops. That is not correct. What is equal? It's equal to omega divided by 2 pi. So plugging those values in, 220 over 2 pi, we get, what do we get? 35 to 2 figures, 35 hertz. Or if you like, 35 oscillations per second. Part 3, on figure 3.1, draw a line to represent the top surface of the piston in the position where the speed of the piston is maximum. Now that, of course, is where I drew the line just before, right in the middle, at the midpoint. So as long as you draw your line at the midpoint, you'll get this mark. Exactly 4 centimeters above the initial position. If the diagram was to scale, you could do that, but certainly the midpoint between the two lines shown. Number 4, calculate the maximum speed of the piston. That's Vmax, of course, we know that to be equal to A times omega, or omega A. Now, the value for omega, 220, and the amplitude was 4 meters. So that's simply 880 centimeters per second. Okay, the next part. We're looking at now we're looking at 3 different cylinders, and you can see them there, X, Y, Z. So we're looking at a difference of phase between the 3 cylinders. If you look at the question quickly, it talks about cylinder Y leading piston in cylinder X by a phase angle of 120 degrees, which is the same as 2/3 pi radians. Then you're asked to complete the diagram of cylinder Y for this instant by drawing 1. A line to show the top surface of the piston, and 2. An arrow to show the direction of movement of that piston Y. Now, to do this, I think the best thing to do is to consider the reference circle. I'll just move this to the side, give me a bit more room. So if we sketch the reference circle alongside, roughly like that. It's not quite matching, but the equilibrium position is across the centre, and the phasor that represents the position of the piston inside cylinder X is starting at the lowest position, which is down there at this point. And of course everything rotates counterclockwise at the rate of omega, the angular frequency of the pistons in this case. So the question is, if the piston is leading X by 120 degrees, that's somewhere up here on the circle, so that angle will be 30 degrees, that's 90 of course, so that's 120 degrees in front of piston X. So that's the position for Y. And the question asks, exactly how far is that? It's asking you to draw a line precisely as possible, I suppose, on the diagram. So to find out this position, you need to find out how high above the equilibrium position. So this side of the triangle here, the opposite side to the angle. We know this hypotenuse, of course, is the size of the amplitude of the oscillation, which is 4 centimeters in this case, and therefore it's just a matter of plugging in to the trigonometrical equation and solving for that height. We'll just call it x or something. So it's simply 4 sine 30 degrees, and 30 degrees, sine 30 degrees is 0.5, so that gives us 2 centimeters above the equilibrium position. Now, if we go back to the diagram and put our equilibrium position roughly there, that means we're here. And you probably want to label distances on this diagram just to show the marker that you know what you're doing. Something like this would be okay, showing that you have the cylinder. You probably want to label this equilibrium, or maybe just extend it across all 3 cylinders. And what does it say? It just says a line. Yeah, so we've done the line, that's all we need to do. Oh, direction of movement. So, since, of course, on this diagram over here, this phasor diagram, this point is still moving upwards to that highest position, then we know that the piston on the diagram here is also still moving upwards. So just putting an arrow like that. Yeah, so perhaps it's not that good to actually have these arrowheads drawn for these distances here, because it might be confusing. So label it clearly is the message there. Now the next part of that question, cylinder Z, the oscillations are leading the piston in cylinder X by 240 degrees or 4/3 pi radians, and they're asking us to complete the diagram of cylinder Z for this instant by drawing. So I can't easily go back, so what I'll do, I'll just reproduce the cylinder here roughly. If this is our equilibrium position, and let's say here is position of X, where is Z? Now, going back to the reference circle again, we know from the reference circle from before that X is at the bottom of the motion. We also had Y in there at about this position, 120 degrees in front. Now, by symmetry, it's pretty obvious that 240 is another 120 degrees on from Y. So this total angle here is 240 degrees. You could also look at the interior angle here, of course, being 120. Whichever way you look at it, it's the same thing. So Z is there. easy with the reference circle. So that means, of course, you could draw that, but just realise that it's come down from the top position up here and gone down, so it's coming back down towards the equilibrium position. Okay, so it's the same position as y, so we'll just put that in straight away, but it's moving down. So that's how you'd label the diagram. You could do this another way. You could use the original equation, d equals minus 4 cosine, and put in 240 degrees, and you'll get 2 centimeters popping out of that. But knowing the 2 centimeters is down or up from the equilibrium position, and the fact that z is moving down, you have to do some more work. You'd have to find the velocity equation, which you could by taking the derivative of the displacement equation. But I think it's a lot more work, so knowing how to use the reference circle for this topic is very, very important, and it simplifies problems like these. So, next question. For the piston in y, calculate its speed for this instant. Now, again, we could take the derivative of the equation of displacement, which they gave us originally, and would end up being something sine of the angle omega t, but since we already know from before the equation that relates velocity to displacement y, and that's a very useful equation as we've seen, plus or minus omega root a squared minus y squared. We know the position y to be 2 centimeters. That's the displacement from equilibrium position, so we can just plug the numbers in here and that would be a lot simpler. So doing that, we have the amplitude 4 squared is 16 minus 2 squared, which is 4. So 16 minus 4 is 12, all square rooted, multiplied by the omega, which we found before to be 880 centimeters. No, sorry, the V, no, that's not correct. Oopsie daisy, that's the velocity, of course, maximum. No, this is, in fact, 220, isn't it? 220 radians per second. Right, so that should be the correct answer. Now, we know it's moving upwards, so we can just take the positive value. So it's a positive value because we know at position y, this position here, it's still moving upwards towards the top of the circle there. So that helps us with the selection of the plus or minus, so we'll just take that, and that gives us, just calculating that, 762 centimeters per second. That sounds about right. It hasn't quite, it's gone past the maximum value at equilibrium, just past it, 30 degrees past it, so it's slowed down from its maximum speed of 880 centimeters per second.